So yes, we're at the final episode. We're going to just wrap up with a topic that is just an introduction to something that you will probably pursue further once you get to things like algorithms, which are common solutions to common problems, like efficient solutions to common problems in programming. And you'll come across algorithms that are recursive. And so recursion is the topic of the day. We're not going to be masters of recursion. We'll have an intro to recursion. We'll understand a bit what recursion is and approximately how it usually works in an algorithm. But we won't be able to, write massively efficient programs that are recursive programs at this point. This is a quote that I thought was important, and it'll make more sense later, but use recursive procedures for recursively defined data structures. Once we see what recursion means and how it solves some problems, I think this will make sense. But very often, as you'll think later in this lecture, I hope, you'll wonder, why would I use recursion instead of a loop, a for loop or a while loop? Because in some ways, a recursive algorithm is similar to an algorithm with a loop. It's a repetitive process. And the answer is you use recursion where it makes sense, where the thing you're trying to loop through is by nature recursive. Bear that in mind, memorize that. We'll get to that a little bit later, once we discuss what recursion even is. It's a concept from math, but obviously computer science is originally anyway a subdiscipline of math. And recursion is a function or procedure, doesn't matter how you code it. It's a function or procedure that is defined in terms of itself. That might not be a very good, helpful definition for some people. Let's look at some recursive humor. Recursive humor, I think, will expose to you the nature of recursion better than anything. A couple of recursive jokes. The Linux operating system, this is not a joke, but the part that is a joke is the name GNU. So what we call the Linux operating system, which is a clone of Unix, it was originally named and is still called by some people GNU, G-N-U. And if you want to know what GNU stands for, it's an acronym that stands for GNU's not Unix. So there you go. You want to know the definition of GNU. GNU means GNU's not Unix. And so then you're wondering, what is GNU? Well, GNU is not Unix. And what is GNU? GNU is not Unix. To get to the meaning of the phrase GNU, the acronym, you have to refer to GNU. And then to get to that meaning, you have to refer to GNU again. You're never going to get the ultimate meaning of what GNU is, because you're stuck in a recursive iteration. The term is defined in terms of itself. So there's no end to this. You're never going to get to what GNU is. All you know is GNU's not Unix. And that's actually kind of a joke, because GNU is actually a ripoff of Unix. So it's not officially Unix, but it's actually a clone, a semi-legal clone of Unix. Anyway, that's joke number one of gives you a sense of recursion. There's a definition of a term that refers to that term itself. Here's a programmer's joke. Now, programmers are not known for being very funny, but to understand recursion, you must first understand recursion. That's a common joke in textbooks about recursion. Again, in order to define the term recursion, you've got to look up what recursion is. You don't really get to ultimately the meaning of what it is, because it refers to itself. Here's a recursive joke. Want to hear a joke about recursion? Anyone?
Sure.
Thank you. Want to hear a joke about recursion?
Okay.
and that's the joke. The joke is that it is itself the joke. So you get a sense of programmer humor, but also particularly recursive humor here, which actually can be kind of funny in that case. So we have definitions of things that actually reference themselves, which doesn't really get you anywhere. But we'll see how we can use that concept in code to solve some problems, and it'll make some sense. The first kind of an example that textbooks love is the example of Fibonacci numbers. This Fibonacci sequence, it's an old sequence from at least the 4th century BC India, and people have been talking about it ever since, and it might even be older than that. But it's a mathematical sequence that kind of puzzled and wondered people, created wonder, and used for various calculations and so on. I'll link to the Wikipedia page, and you can look up the history of it a little more. But it's a popular conceptual sequence of numbers where there's a kind of a fixed algorithm for generating the next number, the next number, the next number in the sequence. And so what is that algorithm? The sequence kind of starts with hard-coded numbers. 0 and 1 are the first two numbers in the Fibonacci sequence. That's a given. You don't argue about that. That's your given numbers that you start with. Every other number after that follows an algorithm to calculate it. After that, you add together the previous two numbers to generate any subsequent number. So the third number, 0 is the first, 1 is the second. The third number would be 0 plus 1, 2. The fourth number would be that 2 plus the previous number, the 2 plus 1, which is 3. Right? So if you look at a sequence, and it keeps going infinitely, but 0 and 1 are your given first two numbers in that sequence. The third number is the sum of the previous two. So 0 and 1, I think I might have misspoken, but the 0 and 1 added together get you 1. The next number is the sum of the previous two. So 1 plus 1 gets you 2. The next number is the sum of the 1 and the 2, gets you a 3. The next number is the sum of the 3 and the 2, right? So you keep going with this. And one of the nice features about the Fibonacci sequence, there are many different ways people use it. But one of the interesting things is that the gap between each subsequent number gets bigger and bigger the higher you go. It has some interesting implications for in some fields. But anyway, it's just an algorithmically generated series of numbers that happens to be used and thought about in computer science in many different ways. All right, so that's the Fibonacci sequence. That's the definition. It's kind of a puzzle, a mind game, a wonderful little sequence of numbers that people have been playing around with for 2,500 years. How would you write an algorithm in code to be able to figure this out? Well, the recursive nature of this, the reason why this is recursive is because if I say, for example, find me the 5th number in that Fibonacci sequence. Now the 5th number, 1, 2, 3, 4, 5 is the 3 here, right? So, but if I said, into a program to try and write a program that can find me the nth number in that sequence, let's say the 5th, then of course the 5th is the sum of the previous 2, the 4th and the 3rd added together, right? So that's what I'm saying here. The nth number in the sequence is simply the sum of the previous 2, the n minus 1 and n minus 2 added together. But in order to calculate, let's say I want the 5th, in order to calculate what is the 4th and the 3rd, well, the 4th is defined in terms of its previous 2, the 3rd and the 2nd. The 3rd is defined as the sum of its previous 2, the 0 and the 1, right? So every number is defined in terms of the previous ones. The previous ones are defined in terms of the previous ones. The previous ones are defined in terms of the previous ones, and so on. So there's a recursive nature to this where every number in the sequence requires you to calculate the previous 2 numbers in the sequence, which requires you to calculate the previous 2 numbers in the sequence, and so on. So there's a recursive kind of a spiraling loop. Let's see how you would do that in math. The way you would write this formula, just mathematically, would be the function to get the Fibonacci number at any given position in the sequence, where n represents what position, would be the Fibonacci algorithm for the previous number in the sequence plus the Fibonacci algorithm for the number at the second closest position. So that's how you'd write that in math. How do you write that in code? Let's look at an algorithm that is recursive, written in Java to do this. I made it static just because it's not a changing behavior based on any given object. But imagine there's a class with this method defined in it. And you've got the method Fibonacci takes an argument, which is what number in the sequence do you want? Let's say 5th, 6th, 7th number in that sequence. We know because the Fibonacci sequence gives you this as kind of hard-coded starting points, that the first number in the sequence is always 0, and the second number in the sequence is always 1. That's kind of the definition starting point of the Fibonacci sequence. So if the n coming in as an argument is a 1, we know that the answer is 0. We don't have to do any fancy operations. If the n is a 2, we know that the answer is a 1, because these are all given. There's no way you would algorithmically determine those. Those are the definition of the Fibonacci sequence. So those are kind of taken care of just with an if statement. So if the number you're looking for is the 1 or the 2 position in that sequence, just return those numbers directly. For any other subsequent number, we can use recursion to figure it out. Let's say this is a 3 that comes in. So it's not a 1, it's not a 2, so it's not the 0 or 1. So we'll recursively figure out what it is. The value in the Fibonacci sequence at position 3 would be the value at position 2 plus the value at position 1, right? So this is recursion. You've got the method calling itself, but actually giving a different argument to the function, but still the Fibonacci function is calling the Fibonacci function actually twice. So that's recursion in terms of programming. You've got a method that calls itself. So the answer here would be the Fibonacci number at position 3 is the Fibonacci number at position 2. Imagine this gets called with a 2 passed in, and that returns a 1. So that's a 1 plus the Fibonacci sequence at position 1. Pass in a 1 and another invocation of this method would return you a 0. So 1 plus 0 gets you 1. So the third number in the sequence is a 1, which you know is true if you look at the sequence. The 1, 2, 3 is a 1 over here. I've written it a little more cleanly with more comments and so on in the documentation up here. So you'll see there's a Fibonacci class which has that Fibonacci method in it. I've given some comments. And if I run it, what I'm doing here is I'm actually looping through numbers 1 through 11 and getting the Fibonacci number at that position. So calling that method we just looked at, passing it the number in the Fibonacci sequence that we want to get the value of, and it will return it to us and print it. So let me run it, and you'll see that we're going to generate the first 11 numbers in the Fibonacci sequence. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So take my word for it, these are correct. And it doesn't really matter what number you put in there, but you can, for any position in this sequence, this algorithm will get you the right value, and it's recursive. If the number is not 1 and 2, it will do recursion, at least 1 or 2 different recursive calls to call that function itself to generate the previous 2 numbers and add them together. Let me take a look at the call stack. So imagine that you asked the program to give you the number in the Fibonacci sequence at the 5th position. The number at the 5th position, just to remind you, is 1, 2, 3, 4, 5, is that 3. So let's say we don't want to hard code the 3, we want to use our algorithm to generate magically that 3. This is a diagram which you can click on to get to a zoomable version of, because it's kind of big and long. This diagram shows you the changes to the call stack. So each one of these vertical blocks, piles, is the stack at a given point in time. So my main method, let's say, is going to call the Fibonacci method and pass it a 5. Right? I'm trying to figure out the 5th value in the Fibonacci sequence, so I call the Fibonacci function, I give it a 5, and it should return to me the 5th value in the sequence. But how does it do that? I'm trying to show you here that when you have the main method call Fibonacci, it triggers another stack frame. There's an invocation of a method. Every invocation of the method leads to a stack frame being added to the stack. Remember that Java is only ever looking at the code and memory at the top of the stack at any given time, the top stack frame. So we've got the argument coming in 5. So this new invocation of Fibonacci, this is the first invocation of the Fibonacci function, is triggered from the main method, and it gets a 5 as its argument. What does it do? It, in the code, says, okay, get the 4th and the 3rd and add them together, and that's what the return value is. So it has to figure out, it starts with the leftmost function call here. When it's trying to figure out what the value here is to return, it has to figure out what each individual value is, and it starts with the one on the left. So it goes and figures out what is Fibonacci 4. So it creates a new stack frame for a new invocation, the second invocation, in this case, the first recursive invocation of the Fibonacci method, passes in the 4 as an argument, and the algorithm says, okay, to figure out what Fibonacci at position 4 is, we've got to figure out what it is at 3 and 2. So it starts with a 3. It's always going to start with the leftmost part of this plus sign. And it's going to pass another invocation of the Fibonacci method, the third one in this case. It's going to pass in a 3, which, of course, the algorithm says, well, the Fibonacci value at position 3 is the sum of the Fibonacci value at position 2 and position 1. So it's got to go figure out what those are. It now invokes a new invocation of the Fibonacci method, the 4th one, passes in that 2. This is what we call a base case. This, in the code, it says, well, if the argument coming in is a 2, return a 1. Remember, that's in the code. It's hard-coded to see if the argument is a 2 that we're looking for. The second value in the Fibonacci sequence is hard-coded at 1. There's no need for recursion. So that's what we call in recursion a base case. We'll talk more about that term in a second. But we've now figured out that we can finally return something, a 1, because we've gotten to an iteration or an invocation of the Fibonacci method that does not require recursion anymore. There's no next method call that has to happen. This method invocation itself figures out the value to return, which is a 1. So where you had a call to Fibonacci and passing it a 2, you now get back in memory a 1 in that spot. Then it's going to move on to figure out what the next thing to add to that 1 is, that Fibonacci with the 1 as the argument. So it's going to invoke the Fibonacci function again, pass it the 1, which of course is one of the hard-coded values. The first value in the sequence is a 0, so it just returns a 0 with no needed recursion. We then return back to the third invocation, and we know now that the return value is 0, so the result of this invocation of Fibonacci, the third invocation, is a 1 plus a 0, which is a 1. Right? So it then returns that to the previous stack frame, where it had previously had a call for Fibonacci 3, it now gets a 1 back. It's figured out that the third spot has a 1. Now to figure out what Fibonacci at position 4 is, it's taking that 1 from the Fibonacci 3 and adding it to whatever Fibonacci 2 returns. Fibonacci 2 calls the Fibonacci sequence. That's one of the base cases. That's one of the values that's kind of hard-coded in this algorithm, and it returns a 1. So now we know Fibonacci 3 plus Fibonacci 2 is actually 1 plus 1. And we can now return that 2 to the previous stack frame. That previous stack frame takes that 2 where it was called, where we had tried to figure out what Fibonacci at position 4 was. We now got a 2. And it has to add that to whatever Fibonacci at position 3 is. It's got to go figure that out. So it triggers a new stack frame the 7th time we're calling the Fibonacci method. It takes in that 3 as an argument. The Fibonacci sequence at position 3 is at 2 and 1 added together. And so it calls Fibonacci, passes it the 1. That's a base case. The value at position 1 is 0. Returns the 0. I'll stop here. But you're going to keep on doing this. And actually, this goes on for quite a bit longer. And ultimately, you're going to call the Fibonacci method 9 times, 8 of those being recursive, because the first invocation of the Fibonacci method is not recursive. It comes from the main method. But the next 8 are actually recursive, meaning the Fibonacci method is calling itself to figure out different values that it's being requested. So ultimately, you get down to a 3. But you can look at this diagram and realize kind of the complexity. The reason why I'm showing this to you is you realize that this is not a straightforward loop. This isn't like a method call in a loop where you call the method 10 times, and then after the top one goes away, you go to the previous one. After that one goes away, you go to the previous one. You're kind of removing and adding to this stack, actually, in a somewhat irregular pattern. It's not like it all goes up, up, up on the stack and then down, down, down on the stack, which is how we've previously seen things happen. We've seen the stack go up and down in any given method call, but never go with one method call to this kind of up and down zigzag sort of a pattern. So that is perhaps unusual and unintuitive to some people. So it takes a bit of time to get used to the behavior of recursion. But studying the stack frames can help. This is not the easiest example. There are easier examples that I'll show you. The formula is, as you can see, quite simple. The the 2 hard-coded values, if the number you're looking for in the sequence is the first number, well, it's a 0. If you're looking for the second number, it's a 1. Otherwise, it's the result of whatever the number is at the previous 2 positions added together. Right? That's a super simple formula, which is why it lends itself to learning about recursion. Let's move on to another example. So my goal here is to show you, and through a couple of examples, to show you that actually recursion often has some properties in common in terms of how you use it to solve a problem. So you'll start to see that. Let's take an example of flipping a string backwards. So you have a string like hello. You can flip it backwards. You know there are some string methods. String builder, for example, has methods, and I think the string class itself has methods to return a version of a string backwards. But what if you wanted to write that yourself from scratch? Recursion actually could be a reasonable approach. Now, if you wanted to write an algorithm to take a string and flip it in reverse, you know that if it's only 1 character long, like my string is E, then I don't really need to do anything because E backwards is E, right? So if the string you're looking at is 1 character or even 0 characters, an empty string, then you don't need to do anything else, just return back the original, right? So if you're making a function that takes a string and flips it backwards, if that string is 1 character long or 0 characters long, you can just return the original and it'll be correct. So there's no work needed to be done in the case where the string length is 0 or 1. However, if your string is more than 1 character, then you can have a recursive algorithm which returns the last character of the original string. So let's say my string is hello, or actually I'll give you an example here of nonplussed. So let's say your string is nonplussed. Well, you know, because you're a human and you're smart, that the nonplussed backwards is going to start with a D, right? That's easy enough to say. You flip this string backwards. Of course, the last character is going to be the first character of the new string. And what you can do is you can say, okay, let's take off the last character. Let's take that D, and we'll just say that nonplussed backwards is the last character plus whatever the rest of the thing is backwards. So I can call the backwards algorithm on the leftover part after I take off the D. So I can take off the D, put it in the beginning, and then say, call yourself, have the backwards method call itself, and pass it everything except that D. And that will get me the backwards version of nonplussed. So let me show you that in code, which might, in some cases, be more straightforward to understand. You might write a method that looks like this. So it's called backwards. You pass it a string, which is being called original. And if the length of that is 0 or 1, as we said, a string that's only 1 character long or an empty string with no characters, you don't need to do anything, just return back the original string, and that's itself backwards. All right, so if you're looking for the backwards of a single character, it's just that character, so just return it. Otherwise, in the case where the length is more than 1. We can figure out what the last character is. I'm using a char just because there's this convenient char at function. I could have made it a string. But you go into the original, get the character at the last position. This is the length minus 1 of that string will give me the index position of the last character. So I'm just getting the last character as a char. That's all I'm doing here. And then I'm getting the remainder, everything except that last character. So going into that original string, getting a substring, what you might call a slice if you were a Python person, and starting from the 0 index up to not including the last index. So everything except the last character will be put into remainder, right? So I've split up the string into the last character and everything else. And then the answer to the question of what that string is backwards is it's the last character in the first position plus whatever the rest of the stuff is backwards. So it's calling it, and that's recursion. You're taking that string, the original string, you're removing a part of it, the last character in this case, and you're doing a recursive call with a leftover. The only way in which this algorithm will ever end is if you get to a point where the length is 1 or 0. Well, let's take a look at the stack frames because I think you might get some sense out of it here. Let's imagine that you're trying to print out the result of the backwards function, giving it a yes. That's the word that you want to pass it. So your main function calls backwards, passes it the argument yes. All right, so the argument comes in, the first invocation of the backwards method has the argument yes, and the algorithm says, the length is not 0 or 1, so we're going to do the recursion, and it's going to take off the last character, s, and it's going to return that s plus whatever the leftover stuff is backwards, ye. Well, what is backwards ye? Well, backwards has to call backwards and figure out, given the argument ye, what is the result of that backwards? Well, ye backwards is the last character taken off, e, plus backwards y, the leftover stuff. That's going to have to call backwards again, pass it the y. We've reached what we call the base case, which is a length 1, where we don't need recursion anymore. We know very well that a 1 character long string backwards is itself. And so our algorithm returns that backwards, which is itself, y. So where you had backwards y, a call to backwards y, you now know that's a y. So you add the e and the y together in the second invocation when it completes and return that. EY gets passed back down to the first invocation of backwards, where you had a call to backwards to figure out what YE was backwards. You got back EY. And you add that to that variable you've been storing S, which then gets returned, SEY gets returned back to main and printed out, right? So you see that any invocation of this method, whether it's the first, the second, third, is always doing the same thing, right? It's always taking some string, chopping off the first character, sending the next batch of stuff, the remainder, to another invocation until you reach the base case, which is length 1 or 0, at which point recursion isn't necessary and you can just start to unfold the stack frames, right? They can start to return to their previous stack frames, the values that they've calculated. This will take some time for you guys to study. So again, if this isn't intuitive, that is absolutely 100% normal. This is one of those things that you're not used to. You haven't learned this. This isn't something that's like a loop. It's kind of like a loop, but it actually, as you see, has behaviors that are quite different. All right, let's move on to calculating powers. So another example. In this case, the problem of calculating powers, or the power equation, is how do you figure out what some base number is to some exponent? So 6 to the 12, for example, or 5 to the 10, or whatever the base and the exponent are. How would you write an algorithm that calculates what that is in terms of just a regular number? And the answer is, we know a couple things, right? We know that if the power is 6 to the 0, for example, then it's a 1, because everything to the 0 is a 1, as you learned in middle school or at some point like that. Right? Anything raised to the exponent 0 is actually 1. So if you're if you're trying to write a function that is an algorithm for calculating the result of some base to some exponent, if that exponent is a 0, you can just simply return 1, because everything to the 0th power is 1. Otherwise, if it's anything more than 1, there's a recursive way we can decompose that problem. So for example, if you're trying to figure out what 6 to the 12 is, well, you know that 6 to the 12 is the same as 6 times 6 to the 11th, right? That's kind of the definition of an exponent. You have 6 to the 11 times 6, that's 6 to the 12, right? So this is the same thing. It's equivalent to 6 to the 12. But this is actually a recursive way of writing it, because if you're looking for 6 to the 12 and you define it as being 6 times 6 to the 11th, well, then you can go figure out what 6 to the 11th is, and that would be defined as 6 times 6 to the 10. And what is 6 to the 10? 6 times 6 to the 9, right? So you have a formula that is a recursive formula that says that a base to any exponent is the base times that same base to one less than the original exponent. And that's a recursive part. The exponent function that tells you what the power is of anything to any exponent is referring to itself. Let's see that in code. I think that'll make it clear. Here's an example of calculating power equation. So you take in some base and you want to raise it to some exponent. And if that exponent is a 0, we know we can return a 1 because everything to the power of 0 is 1. So any base, doesn't matter what the base is, to the power of 0 will just be a 1. So that's easy enough. Otherwise, if you're trying to figure out what anything else is in terms of exponents and bases, then it would be the base times this same function, recursive call to this same function, passing it the base and 1 less than the original exponent. So imagine it's a 6, the 6 to the 12 as the base and the exponent. 6 to the 12 would be returning 6 times 6 to the 11. That would be calling the power function, which would take in 6 and 11, which would then figure out that it's 6 times 6 to the 10. That calls itself again 6 and 10, which calls itself with 6 and 9, which calls itself with 6 and 8, and so on. So you're having each function invocation, each invocation of this power function has a call to itself, as long as the exponent's not 0. And the recursiveness will only ever stop when that exponent reaches 0, which it will do at some point. Let's take a look at the call stack, and you'll hopefully get a stronger sense of this, when it stops. So imagine you're calling 5 to the power of 2. You're calling your power function, passing it a 5 and a 2 and printing out the result. All right, you call the function for the first time. That invokes on the stack frame, a new stack frame for that first invocation, which has arguments 5 and 2. And the program says if the exponent is a 0, which it's not, return 1, but it's not, so it's got to figure out what 5 to the power of 2 is. And the definition of the function says the value to return would be 5 times 5 to the power of 1. And it has to call itself to figure out what that is. So it calls itself to figure out what 5 to the power of 1 is. That invokes a new stack frame, a new invocation of that same method, which has now 5 and 1 as the arguments. It's the second invocation. And the power 5 to the power of 1 is 5 times 5 to the power of 0. That's the definition. So it has to figure out what 5 to the power of 0 is. That is what we call the base case. This is a case where we don't need recursion. 5 to the power of 0, exponent is 0, and we know that we can just return 1. So that's the end of the line for recursion in this case. And we can kind of unwind the stack frames from there. So 5 to the power of 0 returns a 1. So where we had 5 to the power of 0 as a function call, we now got a 1. And that can now return 5 times the 1 to the previous stack frame, which called it. And that puts it in the spot where the original call was. So now we return 5 times 5 down to the main method, which prints out the 25 result. So this is almost identical, really, if you think about it, to the string backwards flipping algorithm. We have a situation where there's a call to a function. The function decomposes the problem, removes some part of what you're trying to calculate, and then does recursion on the remainder. Removes some part and then does recursion on the remainder. And every call is ultimately waiting for you to reach the end of the line where the base case is met, at which point the return values start to add on to each other until you get back to the bottom of the stack. Let's look at this in an abstract sense. So we've seen a few examples. We've seen 3 examples of recursion algorithms, and they're all actually following a very similar pattern. So here's the pattern. They almost always follow a general pattern, and here they are. There's a base case. There's always what we call a base case, which is the case in which the function you're writing doesn't need to recurse. So there's no need for it to call itself. In the Fibonacci sequence, that was when we had a 0 or a 1, a 1 or a 2 as the position in that sequence to find a value at, because the 1 position, the definition of the Fibonacci sequence says that's a 0, and the 2 position always has a 1. So there are these 2 hard-coded values in the Fibonacci sequence. Those would comprise, in this case, 2 base cases, 2 cases in which we don't need recursion in the Fibonacci example. In the example of a string flipping it backwards, the base case was when the string is only 1 character long or 0 characters long, there's no need to recurse. It's backwards version of itself is the same as its forwards version of itself. In the case of the power equation, the base case is when the exponent is 0, we don't need to do recursion. We know anything to the power 0 is a 1, so we just return a 1. Right? So every one of these algorithms will have a base case, which is the case at which, the situation in which, in that function call, recursion is not necessary. And you just return some hard-coded or simple to calculate value. The remainder cases, the other cases are the recursive cases. So if you're not in a base case, if you don't have a situation where you can just return a simple value, you do recursion. But you don't just do recursion on the full original value, you take away some of it. So an example of the Fibonacci sequence, we split it up into 2. We took, the Fibonacci, let's say we wanted to calculate the Fibonacci number at position 5. We didn't just call Fibonacci and pass it to 5. We actually called Fibonacci at position 4 and Fibonacci at position 3 and added them together. So you've decomposed or deconstructed the original problem into subcomponents, and you run recursion on at least one of those subcomponents. In the case of the Fibonacci sequence, we run recursion on both of those 2 subcomponents. The previous 2 values are both calculated recursively. In the case of the flipping the string backwards, we took the last character off of the string, and we did recursion on the remainder. In the case of the power equation, we removed one of the bases, right, 6 to the power of 12. We took out a 6, and we did the recursion to get 6 to the power of 11, which takes off a 6 and does 6 to the power of 10, and so on, until you reach the base case, which is 6 to the power of 0. So those are the 2 kind of cases, the 2 parts of any recursive algorithm. The base case, where recursion is not needed, and the recursive cases, where recursion is needed, but you don't just do recursion on the whole value you're looking for, you decompose or deconstruct the value in some way. And the goal is, at some point by recursing, to reach the base case. Otherwise, your recursion never halts, it never stops. So you have to do the recursive function calls in some way that you're winnowing down the problem until finally you reach the small enough problem that the base case can handle it and you don't need to recurse any further. I just talked through this, but the Fibonacci example, just following the base case and recursive case concept, the base case is when you have a 1 or a 2 as the argument, and in which case you return the first 2 numbers of the Fibonacci sequence, which are hard-coded at 0 and 1. The recursive case is the other stuff. What happens for any other argument value? If it's not a 1 or a 2, you figure out what n-1 and n-2 are in the Fibonacci sequence. So you're looking for the 10th number in the Fibonacci sequence. Well, figure out what the 9th and the 8th are and add those together. Right, so that's the recursive case in the Fibonacci example, where you do need recursion to figure it out. Flipping a string backwards, just in terms of base case versus recursive case, you've got, in this case, the base case is when the string length is a 0 or a 1, and this is a true, and you return the original string. You don't need to do anything. The recursive case is when you don't have a string length 1 or 0, and you have to chop off the last character, get the remainder, and do recursion on that remainder. Right? You've decomposed the problem in some way, and you've done recursion on at least one part of that decomposed problem. In the case of calculating powers, you've got the base case in which the exponent is 0, and you can simply return a 1. And the recursive case, where you do a decomposition, you take out some of the value, in this case, one of the bases, and you then do recursion with the remainder. Right. So that's the pattern that you'll find in almost all recursive algorithms. Otherwise, if you don't have a base case, if you don't have a case that doesn't require recursion, as we've discussed, you'll never stop recursing. The recursive function will call itself, which calls itself, which calls itself, and that will never stop. You'll get stack frame upon stack frame upon stack frame, and ultimately crash your program because of a stack overflow error, which means that there's no more memory for new stack frames to be added. Let's move into fractals. Fractals are something that are tangentially related to recursion, or really they're kind of a sub-discipline of recursive algorithms. Fractals are a category of algorithmically generated images that exhibit a high degree of self-similarity. So this means that you have images that are made up of that same image, which might sound a bit weird, which it is. So let's just look at these for a second. The whole image, the whole picture, can be decomposed into parts that resemble or are identical to the whole image. So imagine an image of a tree made up of tiny trees, and each one of those trees is made up of tiny trees, and so on. So you can have images that have self-similarity or kind of reflective properties where the entire image can be decomposed into smaller structures that are of the same type or identical types in some cases. They're typically generated, these are computer generated or mathematically generated anyway, imagery, and they're typically generated using recursion. So here is, and I had intended to put a third bullet point here, which I think ended up on the wrong slide, so let me just go to that. We will not try to derive the algorithms used to generate fractals, and it says, I think, cut off at the bottom. We're just going to enjoy some pretty pictures, right? So we're not getting deep into fractals here, but I did want to bring it up since they look interesting in some cases, and they're directly tied to kind of a subdiscipline of recursion. So it might interest you. Now, one of the classic fractal images is the Sierpiński Triangle, which looks, it didn't fit very well on my screen when I put it in the slide, so I've made it a link. You can click it to get to the bigger form of that picture. But the Sierpiński triangle here is an example of a fractal image where it depends how you approach the process of making this image, but you can see, if I could slow it down, I think it would be nicer, but you can see that there are triangles being added to every red triangle. So when you have just one red triangle, you draw touching all 3 points, the midpoint of each of the 3 sides of the triangle. You have this black triangle, this big black triangle in the middle, drawn where its corners touch the midpoints of the original triangle. And then that has divided the triangle into 3 red triangles, at which point each one of those has a new triangle drawn touching its midpoints. And that makes more red triangles that then have black triangles drawn to touch each of their midpoints, and so on. So you get a situation where there's a triangle that each part of the triangle has been decomposed into self-similar structures to the whole. So this is a classic example of a fractal image. And this particular animation here is showing you kind of the progressive generation, starting from just one triangle, how you could write an algorithm that would then bisect each of those 3 sides of that original triangle, draw a black triangle, bisect the remaining red spaces, put new triangles in there, and so on. And you can just keep going on that as many degrees or as many levels as you wanted. Again, we're not getting into the math here. We're not getting into anything except just enjoying some pretty pictures, but recognizing that there's a recursive pattern here happening, that there's a repetitive going into each spot and running the Sierpiński algorithm on it, going into each red triangle, running the Sierpiński algorithm on it, and so on. So you see that there are, by running the algorithm, you're generating more red triangles, which then each have their Sierpiński algorithm run on them. And you can just keep going as many orders as you want. Okay. So that's an example of a fractal image. And these are just for your enjoyment. This is not something that we're going to write the code for, or study the math for, or anything like that. Another example is the Koch Snowflake, another classic example of a fractal algorithm. And that looks something like this. This is another algorithm to generate the Koch Snowflake. It creates a sort of snowflake-like shape. So that's why it's called the snowflake. Some people call it flower or something. It has various names, but the Koch Snowflake I've picked as the name. And it is simply an algorithm to figure out how to generate this shape using an algorithm that is recursive. So this one is similar to the previous one, where it starts with a triangle and it essentially bisects each of the sides of that original triangle. Each of the 3 sides get bisected, and the midpoint of each of those 3 sides is then raised up or out, depending on which side you're talking about. You're 90 degrees away from the original line, and a new line is drawn to connect a new point to the first 3 lines. And then you're going to take each of those new lines and bisect them and make little outpourings from there as well. And you're just going to repeat that for every new line you're generating by taking the midpoint, boosting it up, finding the midpoint, boosting it up, finding the midpoint, boosting it up, and just keep running that as many times as you want. This actually can look interesting. As I was looking for nice graphics to show you this, I came across one that was kind of interesting. Let me pull it up. Koch Snowflake Scratch. There's a Scratch programming language, which is a visual programming language, where they had a nice animation that I thought showed you a little bit of the self-similarity aspect of this. There we go. This shows you just a part of the Koch Snowflake, just the top part. Imagine that you're going and running the algorithm. You can see that, I hope you can see that, that this algorithm is just, they're going into more and more levels of the Snowflake algorithm, and it's creating a kind of self-similarity where it looks like you're kind of zooming in, and the more you're zooming in, the more it looks the same. So you're just magnifying by running the algorithm on all the lines and subdividing each line and boosting it out, but you're ending up creating more and more minute details that are exactly like the outermost shape. This is just one corner of it. Anyway, that's kind of interesting. So you have this behavior of recursion, and in this case, algorithmic computer-generated imagery that uses recursion to run the same process on subparts of a shape to generate the subcomponent. Another one that you've probably seen or you've come across, I believe many people would have seen something, would be an image that is derived from the Mandelbrot set, which is a mathematical set. Like the Fibonacci sequence is a kind of a classic set of numbers. You've got a Mandelbrot set of numbers that is more sophisticated, complicated, but still it's a known kind of puzzle that Mandelbrot has come up with, a person named that who has come up with, that people use the algorithm to generate those numbers to generate graphics like this. So you might call this the trippy kind of thing that people love and have posters from and so on. That this is different than the previous in the sense that the self-similarity isn't necessarily exact. You wouldn't say that the closer you zoom in, the more it looks like the outer picture. But there is a self-similarity in the general kinds of shapes that are being generated. So for every given pixel, for every given dot of each of these images, there's an algorithm being run that generates the next picture from each one of those little pixels. And there is a self-similarity that appears, although it's not as direct as the self-similarity we saw just in the Koch Snowflake and in the Sierpiński Triangle. But nevertheless, this is a recursive algorithm that can take every image, any given state of any image, generate from that, using a recursive algorithm, the next image in this animation, and you start to see that it looks self-similar, or it animates and moves in a smooth and kind of somewhat predictable or comfortable manner. All right, we're definitely not going into the math of the Mandelbrot set, but that gives you a sense for the kind of fun that people have playing around with recursion when it comes to generating computer-generated images. And there's, of course, a whole art form of computer-generated art, some of which uses these recursive techniques. And we have reached the end of the line. So the goal here was to give you a flavor of recursion and to get you comfortable with the code examples, those examples I gave you, plus the others I've posted as examples online. So you should have a good set of examples, including the ones I've just shown you, but also some others that you'll notice if you look into them, they're all following the same pattern: base case, recursive case, and figuring out if any given arguments make the function fall into the base case or the recursive case, decomposing the problem in the recursive case, and running a recursive function. So I'll let you poke around those files. There are a couple other examples, but they're of the same general sort. Recursion takes some time to get familiar with, so don't feel like it's abnormal that you don't get it right away. I can't in an hour make you comfortable with it and see what happens when you change them and so on. So that's the way to get comfortable with anything in code, really, especially something somewhat counterintuitive like recursion is for many people. Back to that first quote that we saw on the very first slide, you'll wonder, when do you use recursion? Why would I use it? And this is really the best answer, which is, if your data structures that you're trying to analyze or generate are inherently recursive, then recursion makes sense. So in the case of the Fibonacci sequence, the number sequence is inherently recursive. Every number is based upon the algorithm, the same algorithm used to generate the previous two numbers. So there's an inherent recursion there. Same with flipping a string backwards. Every string backwards is the last character of that string plus the rest of it backwards. So you have some problems where they are inherently recursive. And that doesn't mean that's the only solution to the problem. Sometimes there are, or anything you can do with recursion, you can do without recursion. But very often the recursive code will actually be far cleaner and far easier to understand if the problem itself is inherently recursive. It lends itself to recursion, like the Fibonacci sequence does, like the string backwards, like the math powers do. There are problems where the nature of the problem is easily decomposable into the same problem. And in those cases, your code will be just far easier to write recursively than it would with a whole bunch of loops and if statements if you did it in a non-recursive fashion. In recursion, you often have just base case, recursive case, simple code that breaks things into two different behaviors for any given iteration of a function. So that's really the way to think about it. That's a general rule. Just use recursion where the data structure or the problem you're solving is inherently recursive. And there's no better way to think about that. There are cases where recursion is more efficient in terms of how much processor power it uses. That's not guaranteed to be the case for all problems, but that is sometimes the case. And it's easy enough to time to see how much processor is being used by a recursive solution compared to a non-recursive solution. So when you get into efficiency and algorithms and you're trying to find the most efficient algorithm, there are some general rules, but you can also just time the actual amount of time it takes to run your algorithm and just see which is faster, recursion or not. And that will give you a quick answer as to whether it's the case. It's not always the case, but sometimes it is. And that's it.